Now this is the final block of material, and it's where a lot of the excitement is here in deep reinforcement learning. Now what I'm going to do is talk about the principles of reinforcement learning, the general principles, the foundational aspects of it, and then I will get into some specific examples from the Google DeepMind team. Okay, so let's first start off by some of the theoretical underpinnings, if you will. This is a general reinforcement model. Now we have an environment. The environment is the world in which we're operating in. It could be this auditorium, it could be a factory floor, any environment that we want to do some training in. The agent is going to figure out what actions we should take in that environment. And we're going to always be in a current state and think about moving into the next state, taking an action to evolve into the next state within the environment and within the physical constraints of an environment. And when we take a good action, we receive a positive reward. And if we take a bad action, then we're penalized. So a very high level sort of concept around reinforcement learning. Okay? This is based on what's called a Markov decision process. Now an MDP, the basis for an MDP is that only the current state matters. So I have no history about how I got to where I'm at right now in my current state. I'm only concerned about what the next best action is I need to take to move into the next state. And I'm going to figure out what the best action is that I need to take. And when I take a good action, I'm reinforced by a good policy, a good reward. Now, a Markov decision process is illustrated here. So I'm just giving you sort of the foundational principles that are behind some of these networks we'll talk about, okay? So we define an MDP with states, transitions, actions, and rewards. States are always represented as S. That's where we are at now in the environment. Transition is the probability that you'll end up in S prime. S prime is the new state, given that you took an action and ended up in a new state. And actions are always represented as A. Those are things that are available to do in the environment. And the reward, again, is a value for taking a good action or a penalty for taking a bad action. Now, the solution you derive is a policy, always represented as pi S, takes in a state and returns an action, and the optimal policy is always expressed as pi star, which actions we favor in a given situation. So let's start to think about how to translate some of these principles and express them in various styles of artificial neural networks. So if we're thinking about now machine learning, it's going to be an area of machine learning concerned with learning how an agent should act in an environment so as to maximize cumulative reward. We have agents that observe current state and take an action based on its observation, and the policy is very important. It's going to tell us what the good actions are versus the bad actions. And the environment is often a simulator where we can start to apply these techniques and learn to get better and better over time through a simulator. Now, there are two basic ways of deriving a policy. There's what I'll call a good enough policy with no refinement. You get to a certain level, and that's about it. You're going to stop getting better, if you will. Value learning is about getting continuously better over time through rewards. And this is where on the bottom of the right slide there, the right side of the slide, we're going to find Q state action pairs, Q values. We'll talk about that in more detail, but Q value learning is a key component of the networks we're going to talk about. Now, a good policy should strike a balance between exploitation and exploration. Exploitation is about referring to, for example, a Q table that will inform what the best potential actions might be in a given state. But exploration is a little randomness. Now, if all you do is exploitation, we found that artificial neural networks kind of get stuck, if you will. You need to bring in a little stochasticity in the process, a little randomness to try some things out once in a while and start to inform your rewards using random actions. You get better results. So in deep reinforcement learning, always be mindful that greed is good. And the notion of a little greediness, what we call e-greedy exploration, is something that has shown very good results. That is to bring in a little bit of randomness, and we can set a parameter for that. So for example, if epsilon is 0, that is fully exploitative. I'm only relying on what I think is a good next action. If I do a 0.05, for example, that brings in a little bit of randomness in the process. Okay? All right. Now we're going to talk about, I mentioned the Q value, the importance of that, and that is the basis for deep Q networks and deep Q learning. Now, we could spend 2 or 3 lectures just on the next few slides here. So I'm going to cover this at a very high level to expose you to this. Just recognize that better actions have higher Q values. And we're going to maintain Q value state action pairs in what we call a Q table that you can refer to. We also have something called the credit assignment problem. Which of the preceding actions was responsible for getting the reward and to what extent? That's important to know, how we got our policy reward. Also, what this informs us is it helps to answer this very, very important question. What are the expected long-term rewards given a certain state that we take a certain action, that we do every subsequent action perfectly? Now, in a traditional form, we talked about an MDP, we talked about the basic principles now. The application of those in a general sense do not scale all that well, okay? But there's ways we're going to talk about addressing that problem. Now, here's a very important equation that I provided to you that is the foundation for deep Q learning and deep Q networks. Again, I won't go through a discussion of the notation, but you do have notes there that you can refer to. This is based on something called the Bellman equation. And I've also provided you some pseudocode, and then at the bottom you've got a stepwise description of what that code does. You'll see the equation there, okay? So those are the foundational principles of deep reinforcement learning, of deep Q learning. And now how do you take all of those principles and to start to think about constructing an artificial neural network that can start to learn on those principles? And that is what a deep Q network is. A network that takes you from a state to the Q value of each of the actions at that state. All right, now we're going to get into an example here. This is good work done by the Google team, the DeepMind team. And this is their diagram. So they had a number of ideas around MDP, around some of the ideas we just talked about, those principles, and applying those. Now, the first thing you want to do is try to find a simulator. And so they thought, well, you know, what's available? And they found an Atari 2600 simulator. And there's various games like Breakout that you can play against. And then in their diagram, the brain is the agent, right? That is going to tell us what the appropriate action is we need to take, that we should take in that game. And actions are expressed, obviously, in a game, in this game, by the joystick. And then the console there, the game console, is the environment, the world in which we're operating in. And then it's a video game. So all we have as input are pixels. So reflecting back to our discussion about convolutional neural networks, we could probably expect if the only input we have are pixels, then maybe we need some layers of convolution to understand where we're at in that game as well. So what they did is they took many of their principles and built out a network that looks like this. Now, this is at a very, very high level, and there are papers available that they publish if you want to dig down into great detail about many of the techniques here that I'm not even going to address. There's a lot involved here. But at a high level, what you see is that we have basically, we're approximating the Q function as a neural network. This is so-called approximate Q learning, which is much more efficient than sort of the generic style of Q learning and Q tables we discussed earlier. The convolution layers are similar to what we discussed earlier in convolutional neural networks, but in a sense, what we're doing in the end is learning a reward policy from the inputted pixels. And they have something called experience replay. The agent builds a data set of experience and then takes random samples from that data set. So they are a little greedy, if you will. And actually, what they did is they actually set a parameter of a 0.05. So a little bit of random exploration really helped here in terms of learning. The outputs are Q values, and there are as many output nodes as possible joystick actions. Okay? Now, there's a lot more that obviously goes into this, but very good results. So again, very different than the work I did in the early days in knowledge-based systems, where we tried to take a domain expert's knowledge and code that in a system. Here what we're doing is establishing a learning framework, and then we're going to start off really dumb. And this framework is going to enable us to get really smart and become an expert on its own. So through this process of getting rewards and policy, we're going to learn the game, or the machine rather, is going to learn how to play the game on its own, if you will. So here's a little example of that. So we start off very dumb, okay? And again, we have a little bit of randomness, so we're going to take some random actions initially, and we're going to learn from that. We're going to get policies now and develop an optimal policy. And we're going to learn to get better and better. At 120 minutes, we actually get pretty good. And then at 240 minutes, what starts to happen is, again, through this reward policy and some randomness, and using experience replay, because experience replay now is getting better and better. At 240 minutes, we're getting really good. And we actually understand a strategy now. So in a breakout game, one strategy is you want to break out, for example, on the left side, and then attack the wall from the back. And that's what it does. So it learns to become a true expert, starting off with no knowledge at all, just a learning framework. And that is the basis for deep Q learning. Okay, now they didn't rest on their laurels, and the takeaway for you is while you may have developed a breakthrough capability, you want to continuously innovate. And that's what they did here. They developed something called asynchronous advantage actor critic. I won't get into all the detail, but it's a viable alternative to experience replay, and it leverages multi-threading and CPUs. There's more detail here if you want to look into it, and there's papers that are published. You can delve into that. Okay? Now, there are shortcomings to DQNs. So when the Google team published their papers, everybody got very excited. There was sort of a resurgence, if you will, in reinforcement learning now. But when you come out with this work, then people start to think of it as a Swiss Army knife, and you start to try to throw everything at these techniques. And there are shortcomings you want to be mindful of. First of all, if it's a non-MDP problem, that is, remember, Markov decision problem implies that only the current state matters. But if I need to maintain some history, then these techniques out of the box don't work very well. And if you have a long time horizon problem, so Atari is very tactical. There's immediate rewards coming in. If it's a very strategic situation, like chess or the game of Go, which is very complex with strategic moves and delayed rewards, then you need to change things up a little bit from the original architecture. And then it's simulator dependent. As we saw in that example, they had a benefit of an Atari simulator that you could iterate on and get better and better over time. If you don't have a simulator, either you need to invent one or think about bolting on some other capabilities. So on the non-MDP problem, if you need to incorporate prior actions, you may want to think about one style of network we discussed earlier, which is the recurrent neural network, LSTM. Remember, it has some memory capability, and combining an LSTM with DeepQN might give you at least an initial framework that you can play with. If you have a long time horizon problem with strategic moves and delayed rewards, maybe you want to start thinking about developing a search tree that predicts Q values, for example. So this is work after the Atari challenge. The Google team took on the game of Go. And they built a system called AlphaGo that took many of these principles to see whether they could apply it to the Go game. Now again, this is a little different. It's a slower moving game, very strategic, a huge playing surface, and just a huge number of potential moves and delayed rewards. And what they built out actually has shown good results, and they beat the world champion, Lee Sedol. Now, this is an example of, again, more advanced work and combining different techniques together. And what they did is they reached back to something that was available in the 1940s called Monte Carlo tree search. And they combined that with a DQN, and then there's a lot of other techniques that we won't get into in detail here. But that unique combination of leveraging an old style technique like Monte Carlo with newer techniques has really proven out to be quite effective. And so combining those, they're estimating the future rewards for a particular action and then prioritizing search based upon a guess of future rewards, and that worked quite well. It looks like that at a high level. Monte Carlo always has 4 steps: selection, expansion, evaluation, and backup. There's some notes I've included there, and there's a bunch of papers available if you want to really dig into this. But it's a great example of being very creative, where you've got a breakthrough technique like DQN, and then you're trying to address the shortcomings of it, and you reach back into something that was available from the 40s, like Monte Carlo.